There's only one more issue. Is the pressure term. Pressure is not an independent variable. This pressure is a dependent variable. How? If I take a divergence of this equation, the whole equation, then divergence of this term is 0, divergence of this term is 0. It turns out Laplacian commutes with divergence operator, can show it easily. D by dt commutes with the divergence operator. So these two terms are zeros if I take a divergence. Then we get divergence of the nonlinear term, which is here, equal to divergence of Laplacian P, which is minus divergence of gradient P. So that makes it minus Laplacian P equal to divergence of nonlinear term. Okay, and that's a now I write this in Fourier space. So Laplacian gives you minus k squared, and there's a minus sign here, so it basically is k squared. And the divergence of nonlinear term is ikn hat. Okay, so pressure term is computed like this, and once I have it, I can substitute it here. Okay, so basically we don't need to give P as the initial condition. We can, given velocity field at any time, I can compute pressure. Okay. So this is property of incompressible Navier-Stokes. If it is compressible, then this condition does not work anymore, and we need to compute pressure in a different way. Okay, so that's and well, this equation is ODE now for a given k. We have lots of k's, so we have lots of ODEs, and we can solve all of them by any method which is suitable. Okay, so one such scheme is Euler forward, which is given here. It's like that. Okay, and this equation. So this is a diffusion term, and this is a nonlinear term and pressure term. Now we can also look at the time scales. So time scale, there's a viscous time scale, which is 2a squared by nu phi squared. Viscous time scales are again different for different k's, but this is a max. So this time scale is for maximum k. Okay, or this is a minimum time from viscous time scale, and the nonlinear time scale is h by u RMS. And these are exactly the same arguments as what we did for Berger's equation, no different. Okay. Now, if you look at the ratio, T nu by T nonlinear term, which is u RMS h by nu. Okay. Now, in hydrodynamics, there is one very important particle called Reynolds number. Okay, so you can rewrite this like that: nu times h by L. Okay. Now, this term u RMS L by nu, L is a box size or system size. This is called Reynolds number. Reynolds number. Okay, so and what is this L by H? L by H is n, number of grid points in that direction. We are assuming a cube right now for simplicity, and uniform spacing. In each direction, delta x is same, which is h. So it is Re by n. And okay, now for viscous flows, Re is small. Okay, now I'm not going to tell you about all this, but if you do fluid mechanics, you'll have more discussion on this. For Re small, T nu will be the smaller. Right? Re is order 1 or less for viscous flows. Okay, so T nu will be the smaller of the two. And for viscous flows, we need to choose T nu as your delta T. For high Re, the flow is turbulent, and for that, the Re is quite large. Okay, so Re and N, the theorem that N is Re 3/4, approximately. So if you substitute it here, so Re is bigger than Re 3/4. Okay, so it's Re, in fact the ratio is Re 1/4 and Re is large, so T nu is larger compared to T nonlinear. So which time should I choose? I should choose smaller than 2, right? So I should choose T nonlinear. Okay. For turbulent flows, I should choose T nonlinear, and for viscous flows, I should choose T as T nu. and that's about it. So we will not write a code for this problem in the present course unless you are doing a project. But yeah, so this is a preliminary discussion on Navier-Stokes solution using the spectral method. Okay, so we move on and we go to the Schrodinger equation. Okay, sorry, T is missing equation. Which is really for quantum physics, this is the most important equation. Okay, and for physics too, all of physics, this is one of the fundamental equations. Okay, so we have wave function in quantum mechanics time, and which is a function of x in t or r in t. So I is by partial psi partial t. So this is a time derivative, and right hand side is this is called Hamiltonian. So the kinetic energy term and potential energy term inside. So it's a PD, partial differential equation. Okay. Now you can use spectral method to solve it. In fact, it's quite nice. The structure is pretty nice. So let's first non-dimensionalize it. So h bar is too tiny. My space is also too tiny. Armstrong, all that femto femto, not true. So one for me for nuclear size. So we just scale these two variables, space and time. So t is given by t prime and time scale, which is h bar by EA, and the space RA will come from the system dimension, which I'm not doing here. For a hydrogen atom we solved, we can get RA. Okay, substituted there, the equation is simpler. This partial psi partial t prime. T prime is this non-dimensional time, and in the so the h bar squared by 2m is replaced by alpha, and alpha I thought I would have alpha is here. Alpha is bar squared by this stuff. Alpha is a non-dimensional constant, and v prime is also v prime is v by EA. So it's a non-dimensional potential. Okay, and if I now I do the Fourier transform of this equation, so I get partial t prime partial psi k prime, and this I is going on to the right hand side. So minus I alpha by 2k squared psi k prime, and I now v prime psi I is a product. So again, don't do convolution. It's very expensive. So we just write as a product and then do the Fourier transform. So we go to real space, multiply, and come back. So that's the trick it's used for computing the non-linear term. This is also a non-linear term in some sense. It's a is linear in psi, but v can itself it's let's not put non-linear. It's a v times psi. So it's a product. It's this function of x and this function of x. So it's a product. Okay, so this equation, how do I solve it? So this term can be absorbed by exponential trick into this. Okay. So if I make a change of variable psi k prime to psi k tilde, psi k hat, well, psi hat k to psi hat tilde, and then multiply this by exponential. So these two terms can be absorbed, and this equation looks like that. Okay, so this is a psi tilde, so this is with the exponential term, and if I use Euler forward, then so in fact it's not Euler forward. It's a Adam Bashforth. No, sorry, it's a leapfrog. So leapfrog. Leapfrog, why? Because I want to conserve psi squared dx. So this is what I want to conserve. So psi n plus 1 equal to psi n minus 1. So you just substitute, you leapfrog for this equation and substitute this equation in here. Okay, and we'll get this equation. So we can easily compute, and this is the tricky part is this one, but it's not quite tricky. Once you have Fourier transform functions ready, we can easily compute v prime psi like that. So we can compute wave function psi as function of time. Okay? So straightforward, no issues. We can solve its function of time. Okay. So this for free particle. So free particle v prime is 0. Okay. So my initial condition is this blue function, Gaussian profile. Okay. Now later time, of course, psi is a complex field. So a later time we get mod psi, which is the red dash line. And real part is the blue line. This is real part, real side. Okay. Now we can also compute it exactly. So for the Gaussian profile, we have exact solution, and that exact solution, in fact, is almost on top. So this is exact. These two are exact solutions. Okay? So I made a mistake. The red dash is the red dash are the computed values. So red dash is the computed values, and okay, and this sine curve is the exact value. This one, and the blue curve is the exact value, okay? And they are almost on top. Okay, of course, with these curves, we can't see the small errors. Errors will be maybe 10 power minus 5, 10 power minus 6. Okay, so but it just tells us that the numerical solution is quite good. Okay, please remember that I use leapfrog. Okay, so that conserves the psi square dx to good accuracy. So yeah, so we can get pretty good solutions by numerical method. If you don't like too much of algebra in exact solution, you can just follow numerical solution, which is easy to do. Let computer do all the dirty work. That's the theme.